Hey, what's up guys? Hope you're doing well. I'm Arvind from PrecisionDataScience. Today we're going to be working on aircraft recognition project using remote sensing images. We'll be referring to these two papers from 2020 and 2024 and then build a deep learning model to identify aircrafts. So without further ado, let's dive into the video. First, we're gonna see the dataset. It's available in Zenodo website, and I'll be providing you the link. This dataset was created by researchers from China and then later updated by military experts from Pakistan. In this dataset, we have roughly 9,400 remote sensing images acquired from Google Earth satellite imagery, and we have 20 different aircraft types including B-1, B-2, B-52 bombers, C-5 Galaxy, U-2 spy plane, etc. First, we're going to ignore the warnings to have a cleaner output and then import necessary libraries such as PIL, NumPy, TensorFlow, OS, Keras, etc. to build the deep learning model. Next, we have Matplotlib on Seaborn for data visualizations. We'll set the input dimension to 270. We'll build a CNN model with 3 convolution layers of 32, 64 and 128 3x3 kernels, followed by max pooling layer of pool size 2x2 and stride 2. After the image passes through these layers, it gets encoded into an array of number with the flattened layer. After flattening the layers, we have 2 dense layers with 128 neurons and 20 neurons for the output prediction. The activation is ready for all the layers except for the last case where we have softmax activation for output prediction. We will compile the model with ADAMAX optimizer, which can be beneficial to ADAM optimizer in saving memory and faster training in some cases. We have loss as categorical cross entropy for multi-class categorical dataset with metrics as accuracy. With model.summary, we can see the parameters increasing with the number of filters, and we have roughly 16 million parameters, which is roughly twice the number from the 2020 paper. In 2020 paper, they have achieved an accuracy of 90.66%, and in 2024 paper, they have achieved an accuracy of 97.07 for the training set, 94.81 for the validation set, and 94.44 for the test set. Here they adopted a far deeper model compared to the previous one, hence the improvement. In our current study, we are just using a mid-size model with 3 convolution layers. After creating the model, we'll use image data generator for augmenting the training set and scaling the validation as well as test set. We'll pass the directory location for all these 3 datasets: training, validation as well as test set, with target size set to input dimension and class mode set to categorical. Here we can see that we have roughly 6,000 images for the training set, 1500 images for validation set, and 1900 images for the test set. We'll train the model with model.fit for 40 epochs by setting training set for training and validation set for validation data. And next we'll plot the accuracy and loss curve for training as well as validation set. After that, we're going to save the model with model.save so that we can load it for prediction without having to train it again. Okay, I already trained the model for 40 epochs using GCP, and we have achieved training accuracy of around 96.5% and validation accuracy of 92.69%. Here we can see the curves for the accuracy as well as validation accuracy and the loss curves for training as well as validation set. We have saved the model using model.save so that we can load it for prediction without having to train the model again. Next, we'll be loading the model MTARSI-new.hy and pass it to the training, validation as well as test set for prediction. We can see that we have a training accuracy of around 97%, validation accuracy of 92.68%, and test accuracy of 92.83%. With this, we could get 4th spot in this 2024 paper. As a bonus, let's try to see a similar model trained on a smaller subset of just 6 aircrafts. Again, we are loading a model file, MTARSI new3.h5, and pass it through training, validation, as well as Dataset. We can see that we have a training accuracy of around 96.69%, validation accuracy of 91.66%, and test accuracy of 91.36%. Now let's see a function which uses a model file to make predictions on a sample folder of images. Here we have 6 classes, namely B1 Lancer, B2 Spirit Bomber, B52 Stratofortress, C5 Galaxy, Globalog or the Navy Triton, U2 Dragon Lady. The function is going to load the model and then iterate through sample of images that are resized and then rescaled for prediction. Once the model predicts on the image, it shows the output probability for all the classes. We're going to assign the maximum probability to a variable my prediction probability and respect to class to a variable predicted class. If the prediction probability is more than 80%, then we'll print the predicted class and respective prediction probability along with the image. Otherwise, we'll just print unknown aircraft found along with its image. We'll run this now. First, we have predicted class as B52 Stratofortress with 100% prediction, and it's correct, although this is a blurred version of B52 Stratofortress. Next, we have B1 Lancer with 82%. However, this is not a B1 Lancer, it's a B2 Spirit Bomber, and I think the model is recognizing this based on color. And we have correct prediction for the Globalog with 100%, B1 Lancer with 98.27%. Next, again a Globalog, a blurred version with 100%, and we have C5 Galaxy with 100%. Again, we have a B52 Stratofortress with 94%, a blurred version, Globalog with 98%. Next, we have B1 Lancer with 98.87%, although it's partially hiding inside the hangar. Next, we have highly blurred version of B2 Bomber with 100% accuracy. We have Globalog with 98% correct prediction. We have white B52 Stratofortress with 99.9% accuracy. C5 Galaxy with 100% accuracy, although its mouth is open and I think it's transporting something. And next we have U2 Dragon Lady with 99.89%. This is during takeoff and with 100% accuracy during landing along with the chase car. So this is the same military plane that was controlled by AI for the first time, and I think we built a model to find it. Next, an unknown aircraft found. Oh, this is X-47A and X-47B. So this was not part of the training data, and hence it's not able to recognize this, and it's very rare to find this on Google Maps. Next, we have highly blurred version of B2 Spirit Bomber with 100% accuracy. I think the model is robust in recognizing this B2. Last, we have a Globalog with 99.0. Oh, again we have another rare hydrogen powered drone. It's a Boeing Phantom I that came in the early 2010s, and even I thought this was Globalog based on the wings, but again this is a rare plane. So we have tested our model on some random samples, and we can see the power of deep learning. We have seen that we are getting an accuracy of more than 90%. Now imagine if someone built an AI like the entity from MI7 that could recognize any aircraft flying or stationary in real time. Now the question is not if but when. So that's all I have today, guys. If you enjoyed this video so far, please like the video, share, subscribe and hit the bell icon to see more content. Thank you.